Beneath the familiar blue of the Earth's oceans are hidden worlds of salt and silence. From ancient brine lakes that are sealed beneath Antarctic ice to boiling salt basins deep under the Mediterranean, these are places where time moves slowly, light never reaches, and the water itself is heavier than stone. Here's 20 oceans that exist within oceans. Number 20. The Red Sea Deep Brine Basins. Between Africa and the Arabian Peninsula, the Red Sea hides some of the planet's most unusual deep water, enormous hypersaline basins thousands of meters below the surface. Collectively, they're known as the Red Sea Deep Brine Basins, and they're not small pools but huge depressions formed along the central rift, where the seafloor is slowly spreading apart. Each basin, like the Atlantis II, Discovery, and Kebrit Deeps, form a self-contained ocean within an ocean, with layers of dense salt-saturated water that don't mix with the normal seawater. These kinds of basins were first discovered in the 1960s during deep-sea surveys using the research vessel Atlantis II. They're remnants of ancient evaporate layers. These are massive salt beds that are left behind when the Red Sea periodically evaporated millions of years ago. Over time, the salt deposits became buried and later dissolved by warm hydrothermal fluid that was seeping through cracks in the ocean floor. At depths exceeding 2,000 meters, this water in the basins was extraordinarily dense and hot. The salinity often reaches 280 parts per thousand. That's 8 times higher than normal seawater. And temperatures can exceed 60 degrees Celsius. Because the brine is so heavy, it forms these distinct underwater lakes. Their surfaces shimmer like oil when viewed by remotely operated vehicles, and no oxygen penetrates the layers, creating a completely anoxic environment that is toxic to most life. Now, geologically speaking, these basins are invaluable. They're natural laboratories for studying hydrothermal activity and early conditions of the Earth. These brine sediments are rich in metal sulfides like copper, zinc, and iron that precipitate from the superheated fluids below. Studying these basins helps scientists understand both the chemistry of the ancient seas and how mineral-rich environments could foster early microbial life. From above, the Red Sea looks uniform, but beneath its surface are huge hidden seas of salt water, each isolated, self-sustaining, and chemically unique. Together, they make up one of the world's most extensive hypersaline systems, and remain a reminder that even in familiar oceans, there are still places that function like separate worlds. Number 19. The Black Sea Deep Hypersaline Layer of Eastern Europe. The Black Sea. It's bordered by 6 countries, including Turkey, Ukraine, and Russia, and it is one of the largest inland seas on Earth. And it hides a huge hypersaline ocean within an ocean beneath its surface. Although the Black Sea looks uniform from above, it is vertically stratified, with a thin upper layer of oxygenated water floating over a dense, salt-rich layer that extends downward for nearly 2 kilometers. Around 8,000 years ago, during the end of the last ice age, melting ice caps caused the Mediterranean to overflow through the Bosphorus Strait, flooding the freshwater lake that once occupied the Black Sea basin. This sudden influx of dense, salty seawater sank to the bottom and became trapped beneath a lighter, fresher surface, forming a long-term separation that still exists. The lower 90% of the Black Sea's volume is completely anoxic. It's devoid of oxygen and filled with hydrogen sulfide gas. These conditions make it one of the largest oxygen-free marine environments in the world. This density contrast between the upper and lower layers prevents any mixing, and it preserves this internal, deep ocean. Unlike smaller hypersaline brine pools, this one spans an area over 400,000 square kilometers, making it by far the largest continuous anoxic marine zone. It supports an entirely separate ecosystem down there that's dominated by anaerobic microorganisms. Now, these little microbes perform processes like sulfate reduction, methane oxidation, and they generate unique chemical gradients that sustain the deep-sea life. And the absence of all the oxygen has remarkable side effects too. Organic material like shipwrecks and even ancient human artifacts that sink below the oxygen boundary are almost perfectly preserved, untouched by decay. Expeditions have discovered Byzantine and Roman-era vessels resting intact on the seafloor, their wooden hulls and cargoes shielded from rot for millennia. From a geological and even biological standpoint, the Black Sea isn't a single ocean. It's 2 stacked atop one another. The upper layer interacts with the global ocean through the Bosphorus, while this deeper layer remains sealed, functioning as an independent system with its own chemistry, life forms, and history. It is, quite literally, an ocean within an ocean. Number 18. The Orca Basin, the Gulf of Mexico in North America. Below the warm waters of the Gulf of Mexico is one of the most extraordinary features of the American continental margin, the Orca Basin. It sits about 300 kilometers south of Louisiana. This immense depression goes for nearly 400 square kilometers, and it forms the largest hypersaline basin in the entire Gulf region. It sits at a depth of about 2,400 meters, and it's filled with a dense brine-rich water that's remained isolated for thousands of years. Now, it's formed as a result of the Gulf salt tectonics, the slow deformation of the ancient salt deposits laid down over 150 million years ago during the Jurassic period. These salt layers buried beneath younger sediments occasionally dissolve and migrate, creating these depressions on the sea floor. In the Orca Basin, the dissolution of the subsurface salt produces a massive, stable brine pool that doesn't mix with any surrounding seawater. Its salinity here exceeds 260 parts per thousand. That's 8 times saltier than normal seawater. The interface between these two layers looks like a shimmering reflective surface when you're in a submersible, and it looks like a hidden lake that's resting on the seabed. Below that surface, the water is completely devoid of oxygen. But despite that, microbial life does persist just above and within the boundary. Scientists have discovered thriving communities of bacteria that metabolize methane and sulfur compounds in the absence of oxygen. These microorganisms are genetically distinct from those found in the open ocean, and they've evolved unique ways to survive in this hypersaline condition. For all of its importance, the Orca Basin is difficult to study. The corrosive brine here damages instruments, and it requires specialized equipment to sample without any contamination. Yet, it is one of the Earth's largest and most stable underwater brine lakes, a hidden sea within the Gulf, showing just how much of the planet's oceans are still unexplored. Number 17. Lake Vanda. In Antarctica's McMurdo Dry Valleys, it's one of the coldest and driest places on the planet, is Lake Vanda, a body of water so saline and stratified it forms a natural ocean within a lake. Unlike most Antarctic lakes, though, that are covered in thick ice and fed by glacial melt, Lake Vanda is permanently sealed beneath a transparent ice lid about 4 meters thick. Below this lid is a remarkable layered ecosystem that's been isolated for millennia. Lake Vanda is located in Wright Valley. It's part of a closed drainage system that includes the Onyx River. That's Antarctica's longest river, which flows briefly each summer before freezing again. And because no outlet exists, the salt accumulates year after year, giving the lake this hypersaline character. The temperatures in the deepest part of the lake can reach 25 degrees Celsius, surprisingly warm given the frigid air above. Below 50 meters, oxygen disappears entirely here, replaced by high concentrations of dissolved salts and nutrients, which does form a stable anoxic environment. Unique cyanobacteria and archaea live within the mats within the upper oxygenated layer, forming complex ecosystems that rely on minimal light filtering through the ice. Deeper down, though, anaerobic microbes survive by metabolizing sulfur and nitrogen compounds. Sediment cores from the lake provide a continuous record of the climate history stretching back at least 10,000 years. And each layer reflects shifts in meltwater, temperature, flow, and atmospheric chemistry. And because the lake's waters never mix, the sediments remain undisturbed, and they preserve one of the most pristine natural archives of the continent's environmental past. For some researchers, this place serves as an analog for extraterrestrial oceans and a living reminder of Earth's own capacity to sustain life. In a place that experiences near zero precipitation and relentless cold, this sealed lake quietly endures, a complete miniature ocean preserved in the heart of Antarctica. Number 16. The Dead Sea. Between Israel and Jordan lies one of the most extraordinary natural formations on Earth, the Dead Sea, the lowest exposed point on the planet's surface at about 430 meters below sea level. Despite its name, though, it's not a sea in the traditional sense, but a massive hypersaline lake sitting within the Jordan Rift Valley. That's a deep tectonic depression that forms part of the larger Great Rift System, extending from Lebanon to Mozambique. The Dead Sea stretches for about 80 kilometers from north to south, and it covers about 600 square kilometers. The depth reaches more than 300 meters, and the salinity averages at around 340 parts per thousand. That's 10 times that of the open ocean. It has no outlet. Water flows in from the Jordan River and smaller tributaries, but it leaves only through evaporation under the region's desert heat. Over millennia, this kind of cycle has concentrated the salts and minerals which transform the basin into a brine reservoir dominated by sodium chloride, magnesium, and potassium. Biologically speaking, the Dead Sea lives up to its name in part. Fish and most higher organisms cannot survive here. However, the lake is not entirely lifeless. Extremophile microorganisms like halophilic bacteria have adapted to these conditions. These kinds of microbial communities are particularly interesting to biologists, studying how life can persist in environments that were once thought sterile. Since the 1960s, its water level has dropped more than 30 meters, largely because of upstream diversion of the Jordan River and mineral extraction from its southern basins. As the water retreats, sinkholes have begun forming along the western shore where the underground salt dissolves and it swallows roads, buildings, and date plantations. But beyond all the geology, the Dead Sea has immense cultural and historical importance. It appears in biblical accounts, and it served as a refuge and trading center since ancient times, and it's one of the most visited natural wonders of the Middle East. From a scientific standpoint, it is an open-air lab, a massive hypersaline basin that shows how geology, climate, and time can turn an enclosed body of water into a dense alien sea. Number 15. The Caspian Sea. Sitting on the borders of 5 countries, Russia, Kazakhstan, Turkmenistan, Iran, and Azerbaijan, the Caspian Sea is the largest enclosed inland body of water on the planet. Although often called a sea, it is technically a huge lake covering about 370,000 square kilometers, nearly the size of Japan. Its waters are slightly saline with an average salinity of about 12 parts per thousand. That's about 1/3 that of seawater, making it a transitional system between freshwater and a true marine environment. But beneath the surface, it hides multiple isolated hypersaline basins that do function as self-contained sub-oceans. Over geological time, the water level of the Caspian has fluctuated, sometimes linking with the Black Sea and sometimes shrinking into smaller basins. Today, the northern Caspian is shallow and almost freshwater due to the inflow of the Volga River, while the southern Caspian reaches a depth of over 1,000 meters and shows significantly higher salinity. At the southern end, deep isolated depressions near the Iranian and Turkmen coasts exhibit stratified layers that are similar to other systems. These deep brine zones are rich in hydrogen sulfide and low in oxygen. And although the Caspian isn't hypersaline throughout, these deep basins operate as miniature oceans within the larger sea, geochemically distinct from the upper layers. And the Caspian's ecosystem reflects that difference. Sturgeon and other fish species dominate the oxygenated shallows, while deep sediments host halophilic microbes and anaerobic bacteria. Sediment cores taken from the southern Caspian reveal cycles of salinity change that stretch back hundreds of thousands of years. That's evidence of alternating wet and arid climates across Eurasia. And the whole Caspian has an economic importance too. It has vast oil and gas reserves beneath it, along with significant fisheries and transport routes. Yet the same isolation that created this unique chemistry also makes it environmentally fragile. Rising industrial activity, fluctuating water levels threaten to dispute the balance of salinity and the wonderful ecology there. In many ways, the Caspian's not one sea, but several, each chemically distinct, layered, and partially isolated. It's an ancient remnant of a vanished sea, and a reminder that even the largest enclosed waters can hold multitudes of worlds within. Number 14. Lake Assal, East Africa. In the heart of Djibouti's Danakil Depression is Lake Assal, a gleaming expanse of turquoise and white that marks both Africa's lowest point and one of the most saline natural lakes on Earth. Situated at about 155 meters below sea level and surrounded by volcanic hills, the lake sits at the junction of 3 tectonic plates, the African, Somali, and Arabian plates. They are slowly pulling apart from one another. This rifting not only shapes the region's landscape, but it feeds the mineral-rich waters that make Lake Assal, an enormous natural salt basin, a literal ocean within the desert. Covering about 54 square kilometers, it receives water primarily from underground geothermal springs connected to the nearby Gulf of Chadjura. There's no river inflow here and, crucially, no outlet, meaning every drop of water entering the lake eventually evaporates. As a result, the salinity climbs to extraordinary levels, often exceeding 340 parts per thousand, about 10 times saltier than seawater. Despite this harshness, though, it does host life, though only in microscopic form. Researchers have identified halophilic or salt-loving microorganisms here, including a species of archaea and cyanobacteria. These extremophiles not only thrive here, they also play an important role in understanding how early life might have evolved under similar conditions on a young Earth. Viewed from above, Lake Assal is otherworldly. It's like a brilliant mirror of white salt flats and aquamarine water surrounded by black volcanic rock. It is a place where the boundaries between land, sea, and sky seem to dissolve. A salt ocean suspended in the heart of a desert that continues to reshape itself with each passing year. Number 13. Lake Retba, West Africa. On Senegal's Atlantic coast, just northeast of Dakar, lies Lake Retba, a shallow hypersaline lake that's famous for its pink color. Known locally as Lac Rose, this 3-square-kilometer lagoon owes its color to dense blooms of microalgae that thrive in these high-salt environments. The result is a vivid, shifting palette of colors that ranges from pale rose to deep crimson, depending on sunlight, temperature, and salinity. During occasional storm surges or high tides, the seawater can seep into the lake and replenish the salt, but not enough to dilute it significantly. And that combination of limited inflow, strong evaporation, and periodic marine intrusion keeps the lake's salinity among the highest of any natural body of water, often exceeding 300 parts per thousand. Like Lake Assal, Retba is an active center for salt extraction. Workers here will wade into the shallow pink water to collect crystallized salt from the bottom using wooden tools, coating their skin with shea butter for protection from the brine's corrosive sting. Each year, more than 20,000 tons of salt are harvested, forming gleaming white piles along the shoreline. Historically, Lake Retba has also served as the final stage of the Paris-Dakar Rally, the pink waters forming a great backdrop for one of the world's most grueling races. But beyond this visual beauty and cultural value, the lake is a natural experiment in equilibrium. It is a balance between the Atlantic's inflow and Senegal's dry coastal climate. Recent monitoring has shown that changes in rainfall and sea level could alter that balance, potentially diluting the lake or shifting its chemistry. For now, though, Lake Retba is one of Africa's most recognizable natural wonders, a living example of how isolated saline systems can create miniature worlds that are both fragile and profoundly different. Number 12. Salar de Uyuni, Bolivia. In southwestern Bolivia, the Salar de Uyuni is the world's largest salt flat. It is a blinding white expanse so vast and flat it is visible from orbit. Covering more than 10,000 square kilometers, it is a remnant of a prehistoric lake system. It formed when ancient lakes, notably Lake Minchin and later Lake Tauqua, evaporated thousands of years ago, leaving behind these thick salt deposits and brine pockets. The salt crust averages about a few meters in thickness, and it's composed mostly of sodium chloride, with patches rich in potassium, magnesium, and lithium. Beneath the crust is the hypersaline water with a salt concentration of up to 10 times that of seawater. The composition of the subsurface brine has drawn attention. It holds an estimated 7 to 10 million tons of lithium, about a quarter of the world's known reserves. This metal is crucial for batteries, and it's turned the Salar into one of the most economically significant salt basins on the planet. However, its extraction poses environmental challenges, as the process requires pumping brine to the surface and evaporating it into open pools, which alters the delicate water balance in this region. During the rainy season, though, a thin film of water can transform the salt flat into a mirror-like surface that reflects the sky. It creates the illusion of infinity. Yet beneath that serene appearance, it is a dynamic and evolving hypersaline system. It's a massive ancient ocean turned inside out, where salt, brine, and microbial life can coexist in a land that feels both terrestrial and extraterrestrial. Number 11. Laguna Verde, South America. Sitting on the border between Chile and Bolivia, high in the Andes, near the highest active volcano on Earth, is Laguna Verde, a stunning turquoise hypersaline lake that's sitting more than 4,300 meters above sea level. Despite its name, the Green Lake, Laguna Verde's colors do vary with the light and shifting between a deep emerald and a milky jade. That distinctive hue comes from the suspended minerals in the water, primarily arsenic and copper compounds. The lake's chemistry is extreme. In addition to sodium chloride, it contains high concentrations of borates, carbonates, and sulfates, along with trace metals like lithium, magnesium, and arsenic. Now, these chemical conditions, while toxic to most life, support specialized microbial mats that have adapted to this kind of unique geochemistry. Scientists have found that these microorganisms can tolerate heavy metals and high UV radiation, making this place a valuable natural lab for studying biochemistry. The surrounding volcanoes here do continually contribute mineral-rich dust that replenishes its chemistry, while geothermal activity at the bottom warms localized areas. Together, those processes create a self-contained cycle of mineral concentration and microbial adaptation that's persisted for thousands of years. This lake offers a rare glimpse of how saline, metal-rich waters can interact with active volcanism. That's a combination believed to have been common on the early Earth. But viewed from the air, it is mesmerizing. It's a jewel-like patch of color in an otherwise barren desert. Beneath that beauty is a hidden world of chemistry and adaptation, an isolated ocean where heat, salt, and life coexist in a delicate equilibrium at the edge of habitability. Number 10. Lake Urmia, West Asia. In the northwest part of Iran is Lake Urmia. Once it was the largest lake in the Middle East and among the most saline on Earth. At its peak in the late 20th century, it went on for more than 140 kilometers from north to south, and it covered over 5,000 square kilometers. Today, it fluctuates with rainfall and inflow, but it remains a great example of a large, landlocked hypersaline basin. Now, the lake sits close to tectonic depressions between two mountain ranges that feed it with small seasonal rivers, and because it has no outlet, the salt starts to accumulate as the water evaporates in Iran's semi-arid climate. The result is water so dense that boats will struggle to move through it, and so mineral-rich that the thick salt crusts line the shallows and the islands. This kind of environment only supports a few hardy organisms. The dominant species here is the brine shrimp, whose reddish pigment often colors the entire lake pink or orange when the populations bloom. Over the past 3 decades, however, the lake has undergone some severe decline. Agricultural expansion and irrigation have diverted much of its inflow, while rising temperatures has intensified the evaporation. By 2015, more than 90% of the lake's surface area had vanished, leaving behind salt flats and dust storms. Iranian authorities and scientists have since launched restoration efforts, releasing water from dams and limiting withdrawals to stabilize the levels. But from above, the color shifts from emerald to crimson as the salinity and microbial density change. It's a reminder of the balance between water and salt that defines every enclosed sea. Whether shrinking or swelling with the seasons, Lake Urmia remains a huge world in miniature. Its chemistry and biology are locked in the same cycle that governs the oceans far larger than itself. Number 9. Katitanda, Lake Eyre, Australia. In the center of Australia is Katitanda, or Lake Eyre. It's a huge basin that transforms from a shimmering salt pan into an inland sea, depending on the season. When full, which is a rare event that may only happen a few times each century, it covers up to 9,500 square kilometers, making it the largest lake in Australia. For most of the time, though, it's a hypersaline desert floor, a huge white mirror that stretches across South Australia's interior. Lake Eyre sits in the continent's lowest depression, about 15 meters below sea level, at the terminus of an enormous land drainage network, roughly the size of France. Rivers from as far away as Queensland feed it intermittently, bringing mineral-rich sediments that, after evaporation, leave dense salt crusts. During the dry years, the remaining brine pools reach saline levels about 300 parts per thousand, that's 10 times that of the ocean, and form isolated pockets of these hypersaline water beneath a paper-thin crust of sodium chloride. When the heavy rains finally arrive, the transformation is dramatic. The lake fills with shallow water only a few meters deep, creating a temporary inland sea that's alive with fish and birds. As the evaporation resumes, the salinity rises again, killing most aquatic life and leaving behind these brilliant geometric salt polygons. Beneath the surface are thick deposits of gypsum and halite that record alternating wet and dry epochs that extend deep into the Pleistocene. Scientists are studying these layers and using them to reconstruct Central Australia's climatic history, each band of crystal marking a shift in rainfall, temperature, and even atmospheric dust. Katitanda and Lake Eyre is more than just a salt flat. It's an inland ocean that appears and disappears with the rhythm of Australia's climate. From above, it resembles a colossal mirror that catches the sky. It shows us that even in the driest heart of a continent, the story of water and salt never truly ends. Number 8. The Great Salt Lake in Utah. In the northern part of the state of Utah lies the Great Salt Lake. This is the largest saltwater lake in the Western Hemisphere and one of the world's great inland seas, covering an average of 4,400 square kilometers. It's the remnant of ancient Lake Bonneville, a huge freshwater body that once covered much of the Great Basin region during the last ice age. When Bonneville evaporated about 15,000 years ago, it left behind this much smaller hypersaline remnant, an inland ocean that's preserved by its isolation. Now, the lake sits at an elevation of about 1,280 meters above sea level in a closed basin with no outlet. Water enters from three major rivers, the Bear, the Weber, and the Jordan, carrying dissolved minerals from the surrounding mountains. The immense surface area and the shifting salinity here create a landscape that is both biologically rich and geochemically extreme. Although no fish can survive in the water, dense populations of brine shrimp and brine flies thrive here, feeding on algae that tint the water green, pink, or even deep red. These organisms support millions of migratory birds, including phalaropes, eared grebes, and pelicans, that depend on the lake as a vital feeding stop. But the Great Salt Lake's color changes are famous. A causeway that divides the lake into northern and southern arms restricts water circulation, causing the northern section to become far saltier and more vividly colored. Satellite images show an amazing contrast: blue-green water to the south and bright magenta to the north, showing how subtle differences in salinity can create a distinct ecosystem. The lake also plays a major economic and environmental role. It supplies minerals like magnesium and potassium, supports a thriving brine shrimp industry, and moderates Utah's climate. Yet it's also under stress. Decades of water diversion for agriculture and a warming climate have caused the lake to shrink to its lowest recorded level, exposing lakebed sediments that generate dust storms rich in arsenic and salt. But this Great Salt Lake remains one of the world's largest active hypersaline systems, a breathing inland sea that fluctuates between expansion and retreat. It's a living ecosystem, and it's a geological record. It shows us that even in the heart of a desert, entire marine worlds will survive, sustained only by the salt, the sun, and evaporation. Number 7. Don Juan Pond, Antarctica. With a name that I absolutely love saying, Don Juan Pond is in Antarctica's McMurdo Dry Valleys. It's one of the coldest and driest regions on Earth. Don Juan Pond is a hypersaline body of water so concentrated it remains liquid even when the air temperature goes down below negative 50 degrees Celsius. That's negative 58 Fahrenheit. It measures about 100 meters long and less than a meter deep. This tiny, shallow pond might seem insignificant next to huge salt lakes, but its chemistry makes it one of the most extraordinary laboratories on the planet. Don Juan Pond was discovered in 1961 by U.S. Navy pilots who noticed its dark liquid surface among the landscape. Scientists soon learned that the salinity exceeds 600 parts per thousand. That's the highest of any natural body on Earth. This brine contains extraordinarily high concentrations of calcium chloride rather than sodium chloride, giving it an antifreeze-like property that prevents freezing even at temperatures well below the normal freezing point. The pond occupies a small depression in the Wright Valley where salt will leach from the surrounding rocks and concentrate as the water evaporates. And unlike most lakes, Don Juan Pond receives almost no precipitation or glacial melt. No fish or plants live here, but microbial life does persist. In 2013, scientists confirmed the presence of specialized halophilic microorganisms within the brine and the surrounding soil. Their presence has made Don Juan Pond a key analog for Mars, a planet with evidence of these ancient salt deposits and potential subsurface brines. NASA researchers study it as a model for how life could persist in extreme environments on other worlds. Despite decades of Antarctic climate variability, Don Juan Pond has not frozen solid or evaporated. Instead, it remains in equilibrium, in a delicate balance that's maintained by chemistry, geology, and minimal hydrology. It is one of Earth's smallest oceans within an ocean, yet it is one of the most resilient, a place where salt and water have conspired to defy freezing for millions of years, and it offers a glimpse of what persistence looks like on the very edge of habitability. Number 6. The Aral Sea. Once the fourth largest lake on Earth, the Aral Sea is a huge inland ocean that stretches across the deserts of Central Asia. In 1960, it covered roughly 68,000 square kilometers and contained over 1,000 cubic kilometers of water. But over the past half-century, it's undergone one of the most dramatic transformations in human history, shrinking into a series of small basins that now resemble isolated oceans. Now, the Aral Sea has no natural outlet. Between Kazakhstan to the north and Uzbekistan to the south, it was fed primarily by two great rivers, the Amudarya and the Sirdarya, which once brought snowmelt and sediment from distant mountains. In the 1960s, extensive irrigation projects diverted these rivers to support Soviet cotton production, which reduced inflow to a trickle. With evaporation continuing under the hot climate here, the water level began to drop rapidly, and the lake split into smaller fragments. By the early 2000s, the Aral Sea had lost over 90% of its surface area. The retreat left behind the North Aral Sea in Kazakhstan and South Aral Sea in Uzbekistan each developed their own unique chemical profiles. The northern basin, partially restored through damming and water management, remains relatively saline, while the southern basins have become hypersaline. Halophilic bacteria and archaea dominate, and they tint the water vivid shades of red and orange. These microorganisms here play a key role in cycling nitrogen and sulfur, maintaining minimal biological activity as the ecosystem collapses around them. The drying of the Aral Sea is both a tragedy and a scientific case study. The northern basin has shown partial recovery thanks to a new dam completed in 2005, which traps the river inflow and stabilizes the water levels. But from orbit, what was once a single blue sea now appears as a patchwork of white salt plains and dark briny pools, these little miniature oceans that were carved from what was once one of the world's great inland seas. Number 5. The Baltic Sea Deep Basins. Beneath the seemingly uniform surface of the Baltic Sea is one of Europe's most surprising landscapes, a series of deep hypersaline basins that function as self-contained oceans. The Baltic is the world's largest brackish sea. It's bordered by 9 countries and connected to the North Sea through straits, and its limited water exchange and strong density layering have allowed deep saline waters to accumulate. The most prominent of these basins include the Gotland Deep, the Landsort Deep, and the Bornholm Deep, where depths can exceed 450 meters. Because circulation is weak here and oxygen renewal is pretty rare, the deep water here becomes stagnant and oxygen depleted. Chemically, these deep layers contain elevated concentrations of hydrogen sulfide, ammonium, and methane, making them inhospitable to most life. When inflows of oxygen-rich water occasionally happen through the Danish Straits, they can temporarily reoxygenate the deep, triggering intense microbial blooms. Although not hypersaline in the sense of like a Red Sea brine pool, the Baltic's deep basins operate on the same principle. Density stratification and isolation create stable chemical oceans beneath the surface, each with its own chemistry, microbial life, and environmental dynamics. Seen in a cross-section, the Baltic is a layered world, a fresh, oxygenated upper layer supporting fish and plankton, and a dark, saline abyss where life persists through chemistry alone. It is a complex and powerful example of how stratification can turn even temperate seas into environments as extreme as any desert lake. Number 4. The Sea of Okhotsk brine pools. On the edge of the North Pacific, between Russia's Siberian coast and Japan's northern islands, the Sea of Okhotsk conceals some of the coldest and most remote basins on Earth. Now, the sea itself is largely enclosed by land and ice for much of the year. Cold currents and heavy seasonal ice cover make it one of the few subarctic seas with permanent deep brine accumulations, and expeditions using Russian and Japanese oceanographic vessels in the 1980s and early 2000s showed several isolated depressions containing hypersaline water. These pockets, though not as saline as the Red Sea or Mediterranean brine basins, are denser than the surrounding seawater, and they're stratified enough to create a stable, oxygen-poor layer. The shelf and basin contain thick layers of minerals left from ancient inland seas that once occupied the area. Over time, faults and fluid seepage have allowed the salt-rich groundwater to percolate into these deep basins, gradually creating these pockets. Chemical analysis of samples retrieved by submersibles showed that the brines are rich in chloride and magnesium ions and have reduced oxygen concentrations. These conditions support microbial communities, and their metabolic byproducts contribute to the accumulation of hydrogen sulfide in the deep layers. That's a trait that's shared with anoxic zones in far warmer systems. Though largely inaccessible and rarely visited, these basins remind scientists that hypersalinity is not confined to hot, arid regions. Even in subarctic seas covered by ice and storms, the planet is quietly producing new salt oceans of its own. Number 3. Lake Van, Turkey. In eastern Turkey, surrounded by volcanic mountains and ancient forests, is Lake Van, the largest lake in the country and the biggest soda lake in the world. Unlike most saline lakes dominated by sodium chloride, this one is alkaline and rich in carbonate and bicarbonate salts, creating a chemistry unlike any other large lake on Earth. It covers about 3,700 square kilometers and it can reach a depth of over 400 meters. It is an inland sea entirely cut off from the global ocean system. The surrounding volcanoes still influence the chemistry here by releasing minerals and altering the water inflow. Without an outlet, evaporation slowly concentrates the dissolved salts, and the lake's pH rises above 9.7. Cyanobacteria and haloalkali-philic archaea flourish here, forming microbial mats and layered carbonate structures along the shallows. The sediments provide one of the most continuous paleoclimate archives in Eurasia, and because the lake has remained stable for hundreds of thousands of years, each layer of silt and carbonate deposited at the bottom tells a story of past rainfall, volcanic eruptions, and even human settlement patterns in Anatolia. Drilling cores from the lake have revealed evidence of repeated climate shifts and fluctuations in water level linked to glacial and interglacial cycles. And from above, it stands out like a dark blue expanse in an otherwise dry region. Up close, the shores are lined with mineral terraces and thermal springs where chemistry and geology are constantly reshaping one another. For scientists, it is a spectacular natural wonder, a huge ancient ocean isolated in the mountains, still evolving in quiet isolation after hundreds of thousands of years. Number 2. The Mediterranean Deep Basins. Beneath the calm blue surface of the Mediterranean is one of the Earth's most remarkable hidden landscapes, a network of enormous deep water basins that together form the largest collection of brine pools in the world. These depressions are scattered along the Mediterranean ridge between Crete and the North African coast. They were discovered in the 1980s and remain some of the most alien environments on the planet. They include the Atlante, the Bannock, the Urania, the Tiro, and Discovery basins, and each spans several square kilometers and lay more than 3,000 meters below the surface. These basins originated from the Messinian salinity crisis. This was a geological event about 6 billion years ago when the Mediterranean Sea became almost completely isolated from the Atlantic, and it began to evaporate. Over several 100,000 years, it dried to a fraction of its former size, leaving behind layers of salts up to 2 kilometers thick. When the sea later refilled, these buried deposits became reactivated as tectonic movements fractured the sea floor, allowing these dense brines to accumulate. The resulting oceans within an oceans are unique in chemistry and ecology. Each basin has its own chemical fingerprint. For example, Atlante is rich in magnesium chloride, Urania, hydrogen sulfide, and Bannock in sodium and potassium salts. These differences mean that each basin supports distinct ecosystems, separated not by geography, but by chemistry. At the interface between the brine and the overlaying seawater, microbial mats thrive on the gradients of salinity and sulfide. These bacteria and archaea survive without sunlight, using a chemical reaction involving sulfur and methane. This is a process called chemosynthesis, and below this layer, where oxygen is absent, the water is almost sterile. Viewed through submersible cameras, these basins look like shimmering mirror lakes at the bottom of the ocean, and their surfaces undulate as if made of oil. They are huge, silent, and self-contained, and they're proof that the Earth still hides entire oceans within its oceans, each one following its own chemical laws beneath the surface. Number 1. Lake Vostok, Antarctica. Sealed beneath more than 4 kilometers of solid Antarctic ice is Lake Vostok, the largest and most mysterious subglacial lake in the world. Stretching about 250 kilometers in length and up to 50 kilometers wide, it covers about 12,000 square kilometers. It's comparable in size to Lake Ontario. It represents one of the most massive bodies of liquid water on the planet, completely cut off from the atmosphere for at least 15 million years. Now, Lake Vostok was discovered in 1996 through radar and seismic surveys conducted beneath the East Antarctic ice sheet near the Russian Vostok station. Scientists found that geothermal heat from the Earth's interior and the immense pressure of the overlying ice keep the lake liquid despite the surface temperature. The water beneath is believed to be extraordinarily pure, derived from ancient snow that melted under pressure and refroze at the lake's roof, forming a closed system. Scientists believe this isolation could have allowed microbial life to evolve independently, adapting to high pressure, complete darkness, and low nutrient levels. In 2012, after decades of careful drilling, Russian researchers reached the upper layers of the lake and recovered frozen samples that contained DNA sequences from previously unknown species. While these results are still being studied, they strongly suggest that life exists even in the most extreme of environments. The sediments at the bottom of the lake are believed to hold an uninterrupted climate record spanning tens of millions of years, including evidence of past glacial and interglacial cycles. Plans are underway to access these sediments using sterile techniques and minimizing any contamination of a system that has remained untouched since before the rise of humanity. Lake Vostok is often described as a time capsule from the Earth's deep past, a hidden ocean that's locked beneath ice. It does represent the ultimate ocean within an ocean. It's an entire ecosystem that's sealed beneath Antarctica. What lies beneath its silent waters may not only deepen our understanding of the Earth's own extremes, but also guide our search for life beyond our planet, on the icy oceans that likely exist beneath the surfaces of Europa and Enceladus.